I didn't look carefully, but it's in from 1.1, correct?
Yeah, it's the last problem.
Okay, very good. We'll get to it today, promise. Okay, first of all, I just quickly want to graph x to the fourth so I don't forget. So remember when we graphed x squared, because this is even power. So x squared and x to the fourth are very similar. So here's the graph of x squared. And this x to the fourth, when I want to find the x-intercepts, when I set it equal to 0, because it has degree 4, it will have 4 solutions. You can say 4 solutions? Yes, 4 solutions. They're all the same. However, all 4 are x equals 0. And in this case, it will cross like this one crosses, but much slower at the origin. So it will be something like this. Slow, 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 up. So this is the difference between x to the fourth and x squared. So I can share my screen. Sorry, I wasn't prepared. I should have done this. I messed with the with my tablet for the book. And I should have had this up and not make you wait. My apologies. So you can look and see the difference. One is much slower. So in y equals, clear if you have anything else. So yes, we looked at these functions last time, the exponential functions. So now if you graph x squared, and then you graph x to power 4, you will see what happens. I'm going to use the zoom 6 just to make sure. And as you've noticed, let's go back for a second. Purple, I think it's purple or dark blue, and red. Ready? So zoom 6. Here's the purple. Quick. And here is, okay. So it is, it appears to be narrower as the graph. I didn't use any points. I just wanted to emphasize that what happens here around the origin. So if I want to zoom in, which I would like to, I go to the viewing window and I just want to see anything between -1. That's what I'm more interested in. No. Sorry. So -1 and 1 and -1 and 1 and graph. See, this is the blue, and look what happens. That's what I'm trying to show. I didn't go that far up. So I'm wanting to show you that this is x squared, and look how long it takes x to the fourth. Only one x-intercept. They're all all the same, right? So look how long it takes from, pretty much from here, it gets closer and closer and closer and closer. Okay, crossing. And now further away, but tiny away, till finally moves away from the origin. So this is what happens when there are 4 solutions that are identical. Okay, enough of that. I just wanted you to see the difference. Okay, so now we are ready for other questions if you have before chapter 1. And now we are starting chapter 1 if you don't have anything else for me. I forgot to ask, can I recycle this or we still need it? Any questions on this? Okay, it's recycled then. Okay, anything else for me? Anything? Any questions? Okay, so in that case, let's start with chapter 1. And chapter 1 is all about a process. I don't even want to write it, but I'm going to write it. I'm not going to talk about it today. We're not there yet. But the chapter 1 deals with differentiation. Not yet. We have a lot of preparation before we even talk about this again. So in 1.1, we're going to talk about limits. Again, what is this? We'll see in a moment. Okay, so let's take a look at a function. So I'm going, and then we're going to look at, if you want to bring up your book, and I will bring up mine, and we're going to look at some graphs in the book. Okay, so here's one graph. I have a function. So this is function f of x. I'm going to put some numbers in. I'm just going to make them up. I'm going to say that this is 3. And I'm going to say that this is 4. So somewhere here, when x is 3, the function value is 4. Okay? One more example, the same function. I'm going to copy the same function again. It may not look perfectly the same, but I'm going to try. But this one has a hole. Yes, of course, at 3, 4. Okay, so it's an open point. Okay, so let's take a look at this function, and stop me if you have any questions, anytime, please. Okay, I claim that if x gets closer and closer to 3, for example, 4, 4.5, forgive me, 4, 3.9, 3.5, 3.2, 3.1, that's what I mean by x getting closer to 3 from higher values, or x gets closer and closer to 3 from lower values, 2, 2.1, 2.3, 2.9, I claim that at the same time the function values get closer and closer to 4. So as x at the same time, or just one side, it doesn't matter, one side or the other. So as x gets closer and closer to 3, would you say that the function values, would you agree that the function values get closer and closer to 4? Everyone, would you agree?
Yes.
Perfect. Now let's take a look at this one. Now I want to ask the same question. As x gets closer and closer to 3 from either side, can I say that the function values get closer and closer, closer and closer to 4?
Yes.
Would you agree?
I mean, it doesn't exist there, right?
So one more time. The key words are closer and closer, or approaches. So as x approaches 3 from either side, can I say that the function values approach 4 from either side?
Yes.
Perfect. Can I say that as x approaches 3 from either side, the function values approach 4 from either side? What do you think?
It approaches it, but it's just never going to reach it, so I don't know if it counts.
When I say approach, I mean it does not equal. We mean what we say. So when I say approaches, I really mean it does not equal to. This is mandatory. So one more time, as x approaches 3 from either side, will the function values approach 4 from either side?
Yeah.
Yes. In both cases, the answer is yes. So how do we write this concept? And we have an operator. And now maybe we've never even mentioned the word operator. We will mention it now. So let me give you, before I pull that paper, so let me give you examples of operators. So you understand that this is very similar to any other. So one operator is the square root. Square root. How come? What is this? What is an operator? It does something to a function or to a variable. What does it do? The square root of 9 equals 3. It applies a mechanism, an operation. An operator is applied to 9, and the answer is 3. What is the operator? The square root. Here's another one. I know we haven't talked about this, but I'm sure you have seen natural log applied to a function, to whatever. It's an operator, it is applied to a function, and we get some sort of result. This is another operator, natural log. But the reason I'm giving this example, you can say, what are you talking about? Just talk about limits. Yes, I am talking about limits, but I just wanted to make you understand that when I apply the operator, any operator, to something, then I drop the operator. It's gone because I apply it to 9. I applied it to 9, I got 3. So what does this have to do with what we're showing in a moment? Okay, a lot. So when we, instead of writing that as x approaches 3 from either side, the function values get closer and closer to 4, we have an operator that does that. And the limit operator, the limit of the function f of x as x approaches a, any number, in my example is 3, is L. This is how we write it. How do we read it? The limit of f of x when x approaches a from either side, comma, is L. The limit of f of x as x approaches a from either side is L. This sorry, I'm in class. I have to call you back. Sorry. Bye. It's about a friend of mine who's 86 years old and she's not in good shape. Sorry about that. So when x approaches a from either side of f of x is L. The limit L, the limit L means it exists. L must be a number. Must be a number. If it is infinity or negative infinity, we will say basically that it does not exist. What is the limit? The limit does not exist if the answer is infinity or negative infinity, and there is another option, which is D and E. What does this mean? Does not exist. There is a third way in which a limit does not exist. This is one, this is the other, this is the third. So for the limit to exist, L must be a number. If you say the limit is maybe around 5 or maybe around, no, you have to give me the number. If you cannot give a number, the limit does not exist. We do have something called left hand limit. So the limit of f of x as x approaches a from the left. So it's a power that is minus, which means with smaller values than a. Smaller than a. So this is the left-hand limit. Of course, it has to be a number if it exists. It could be infinity, but it will be considered that it does not exist. But still, if it's infinity, I cannot write dne. If it's negative infinity, I cannot write dne. I will show you examples when we write dne, and we cannot write anything else. So, any questions? Go ahead. Zainab, go ahead.
Did you say that the limit does not exist when it's at infinity and negative infinity?
Correct.
Okay.
The limit must be a number. Yes. If it is not a number, we say it does not exist.